All right, here's a neat example that can help illustrate how exactly the fundamental theorem of homomorphisms works. So before we actually do the proof, let's actually draw some pictures and see what's going on here. So we're going to call this group here the group G prime of complex numbers of that form under multiplication. And so let's have this diagram. We've got G maps to G prime. This is going to be the map eta, as in our the diagram in the textbook. And then we're going to have this map. This is going to come down. I'm going to make it, I'm going to kind of squish it because we have more wide room than up and down room, but yeah. So this is G mod K. And we have this map here, and this is going to be eta bar, and this is new. So what are we going to, how do these maps work? Well, what we're going to do is we're going to take an element of G. G is just the rational number, so we're going to write it as theta plus n. Theta is going to be an element of the rationals intersected with 0 to 1, and n is going to be an integer. And it should be clear that any rational number can be written in this form, and it can be written in this form uniquely. So anyways, this map that when we mod out by k, where k is z, this is going to map this to just theta. And then G mod k is going to map theta to e to the 2 pi I theta. Now, just as a point of reference, if there's like no thing at the beginning of the arrow there, that means that this is this just tells you what the sets are. So this tells you the domain set, and this tells you the codomain set. Whereas if you've got this bar here, then that tells you what this map does to every single element. So if you have an element in G mod K and you call it theta, then it's going to get sent to e to the 2 pi I theta. Okay, so that's what these two maps to. What does this one do? This sends theta plus n will go to e to the 2 pi I theta plus n. But of course that's e to the 2 pi I theta, and you multiply that by e to the 2 pi I n. But e to the 2 pi I n for any integer n is just going to be 1. So this is e to the 2 pi I theta. So this is basically, and of course like these two things are equal. So this is basically the main idea of the argument, is that you look what happens to these elements, and like, oh, theta plus n, it can go to theta, which goes to e to the 2 pi I theta, or you could just send it away straight away here, and the n dies off in this process. And this step here is kind of how you see that that this eta is a homomorphism, and blah blah blah, so forth, bunch of words. So let's do the words now. So by the fundamental, maybe I should capitalize this, maybe I shouldn't. Who knows? Who cares? Theorem of homomorphisms to prove that what we want to prove is that eta bar is an isomorphism. That's what's asked in the problem. It suffices to prove that eta is an epimorphism with kernel K. This was actually, I believe, the corollary to the fundamental theorem of homomorphisms, but whatever. Also, epimorphism, I don't know if that's a common term. I hadn't heard it before reading Jacobson. That's basically just a surjective homomorphism. So it does shorten the language a little bit. The other one that Jacobson uses is a monomorphism, and that's injective homomorphism, and that's kind of easy to remember because like mono as in one, as in like injective is like they're sort of like a 1-to-1. Yeah, because injectivity is 1-to-1, and so monomorphism. So that's kind of an easy way to remember that. And then epimorphism, I don't know what that is. It's the other one. Oh, process of elimination must be surjective homomorphism. So anyways, let's prove these things. So to prove that K is the kernel, if n is in K, which is just Z, then what is eta n? Eta n equals e to the 2 pi I n, which is just 1, which is the identity of G prime. Let's see here. So then I'm realizing now that this only shows us that the integers are contained in the kernel, so we have to do the other way. So let's see here. So let's see here. We know that the integers are contained in the kernel. Then if no. Yeah, K is the kernel, right? So K is contained in the kernel. So if eta of Q is 1, then the only possibility is that let's see here. So eta Q is 1. Then that must be that right, that should basically do it. Then if we write Q equals theta plus n, where theta is in rationals intersect 0, 1, and n is in Z, then e to the 2 pi I theta, e to the 2 pi I n, which is just e to the 2 pi I theta, this must equal 1, which implies that theta must equal 0, because that's the only way for this equation to hold. And so Q is in K, because K is the rationals. Hence, K is indeed the kernel of eta. All right, and unfortunately I have to scroll down past our picture, but hopefully we'll survive. We might not. Anyways, what about epimorphismness? Let's see here. So if e to the 2 pi I theta is in G prime, then theta must be in Q intersect 0, 1, which is a subset of Q. So then theta goes e to the 2 pi I theta. So eta is surjective. And finally, we got one more thing, and that's the homomorphism thing. And that's if A and B are in Q, then eta of A plus B is e to the 2 pi I. I'm not even breaking it up into the different parts, like the one that's an integer and the one that's not. I really don't care for this. E to the 2 pi I B, and that's just eta A, eta B. And hence, G mod K is isomorphic to G prime. And that's exactly what we wanted to prove. So we're done.